The Brayton cycle inspires another type of cycle or another type of engine called the ideal jet propulsion cycle. The Brayton cycle on a TS diagram looks like what you see on the left-hand side, and the ideal jet propulsion cycle looks very much like it. If you compare the two figures, you'll notice that they look almost identical. The only difference is some of the states are renumbered, and there's a couple of extra states on the isentropic compression and isentropic expansion processes. So we're going to push the gas turbine cycle aside and bring over a jet engine to consider how this would work and what all this represents. So notice we're not even talking about a PV diagram anymore, because really the TS diagram is where we want to focus our efforts. It's what really tells us the most information. So from state 1 to state 2, that's a diffuser section of the jet engine. We're going from left to right, where the air goes, and it looks more like a nozzle, but in the real world it'd be more of a diffuser, where the area of flow expands so that the incoming air slows down, and some of its kinetic energy is converted into thermal energy. Now this would ideally be a reversible adiabatic, in other words isentropic process, that could simply be reversed with an appropriate nozzle after the diffuser. But so it's an isentropic process, and then there's the compressor section from 2 to 3. You see all the blades there, whose job it is to compress the incoming air further. Now the diffuser compresses the air some, just because kinetic energy is being converted into flow energy, or essentially pressure. But from 2 to 3, there's blades here. You can't see them, it's sort of a cross section, but there's a shaft going through the engine. All this is in pink, and the turbine at the very end, which we'll get to later, is turning the shaft to drive the compressor. And what you got to understand about a jet engine is that the turning of the turbine and the compressor, you're not really trying to extract much shaft work here. You're not trying to get a shaft to turn where you can put a generator on it or something, although there is some of that, which we'll talk about in a minute. But mainly the job of the turbine is to drive the compressor. That's it. And so what happens then from 2 to 3 is the final compression of the air occurs, so that looking at the TS diagram, we are now at state 3 after exiting the compressor. And then we go into a burner section, a section where fuel is squirted in, the temperature is very high, ignition begins and just continues as long as you keep squirting fuel in and providing compressed air. So this is a constant pressure burning process, because this section is basically just open. I know there's some holes drawn there, but those just represent fuel being sprayed into a combustion chamber, where burning can occur, and hopefully occur efficiently, as the air moves across from left to right from state 3 to state 4. So this is a constant pressure, this is a constant pressure heat addition process. From state 4 to state 5 is the turbine section. That's where the air actually does work, turning the turbine blade so that it can drive the compressor. So from state 4 to state 5 is an isentropic expansion process in a turbine. And then finally from 5 to 4 is the whole reason you build the whole thing in the first place. That's the that's the isentropic expansion in the nozzle. Now this is a really impressive process here from state 5 to state 6, because what you've got at state 5 is air that is still at a reasonably high temperature, reasonably high pressure, going through a nozzle where the flow is being necked down, and so the velocity of flow has to increase. And remember, what a nozzle does is change enthalpy essentially into kinetic energy, and this generates a heck of a lot of kinetic energy, which is why jets are able to fly so fast. The air coming out the back of these things is just unbelievable. Mythbusters, you may have seen, had a taxi video where they blew a taxi around that was being towed behind an aircraft with its engines at high throttle. So the wind coming out of the back of these things is nothing less than a hurricane. It's probably, well, definitely a lot stronger even than that in that concentrated region. So from 5, I'm not saying that a jet engine is stronger than a hurricane. I'm just saying that the wind in that area goes faster than hurricane speeds. So from 5 to 6, that's the business end of this jet engine. And then from 5 to 6, or excuse me, from 6 to 1, coming back around, you'll notice that we've got a constant pressure heat rejection process labeled here. And the idea is that Of course, in the real world, the air coming out the back of the nozzle would cool down and could be reintroduced into the intake of the next craft coming behind them, if you will. Of course, there's all kinds of problems with vortices and things, but anyway, we're going to model that as a heat exchanger that takes the air off of the nozzle, cools it down at constant pressure, and puts it back in to state 1. Now, what about the math associated with this? Well, it's kind of nice because we can essentially use the same equations we had before for the Brayton cycle, because forget state 2, right? I mean, 1 to 3 is still isentropic, 4 to 6 is still isentropic. We don't have to worry about the intermediate states of 2 and 5. 1 is related to 3 isentropically, and 4 and 6 are related isentropically. And we can use constant pressure heat addition, constant pressure heat rejection, and then our energy balance on those devices. And in fact, this energy balance, you might notice, is an open energy balance for open systems because it's got enthalpy. But now we've also got kinetic energy, because there's a couple of devices here where the kinetic energy change is significant, and that's in the diffuser and the nozzle. So our energy balance is a little more complicated than what we had with the Brayton cycle, just because it includes kinetic energy. Now we can still use our isentropic equations, and pressure ratios are good to use here. They're fairly easy to use most times. Our energy balances for heat addition and heat rejection, and then a isentropic equation for expansion through both the turbine and the nozzle is useful. So there's our energy balance for the heat rejection I've already mentioned. However, we really need more detail. The process in the diffuser and the process in the nozzle are both important processes, and if we were to write an energy balance for the diffuser, first of all, we'd notice that the enthalpy change across the diffuser is equal to the kinetic energy change across that diffuser. Now, most of the time, the kinetic energy leaving the diffuser is small, it's negligible, so most of the time we would cross off the kinetic energy leaving the diffuser and going into the compressor. So this is another very useful equation for dealing with jet engines, or at least idealized jet engines. We can also write an energy balance for the nozzle, which you see here, relating the enthalpy change across the nozzle to the kinetic energy change across the nozzle. Now again, a lot of times the incoming kinetic energy at state 5 is small by comparison to the leaving kinetic energy at state 6, and so often we will neglect it. But again, here's a useful equation for dealing with the jet engine cycle. Now here's something that's really important. As usual, you need to find the TS diagram for the ideal jet propulsion cycle in your book. You probably won't find a PV diagram. I don't think your author has one, if I remember right. You don't need it anyway. And wherever you find that cycle diagram, you need to write down the equations that I've had on this slide. There's one more that you need, though, because remember I mentioned that the whole point of the turbine is to drive the compressor. Well, when you're talking about an engine that makes 10,000 horsepower, which is not unreasonable for a jet, is a couple hundred horsepower for some hydraulics for things, or maybe a 100 horsepower for air conditioning, I don't know. Is that significant? No, obviously not, right? When you're talking 10,000 horsepower and you're pulling off a couple hundred, maybe even 1,000 horsepower for flying other things in the plane or making other things work, that's not really significant. So one of the assumptions we make to idealize this is that the work produced by the turbine is completely consumed by the compressor. So W sub turbine, all the work per unit mass in the turbine, equals all the work consumed per unit mass in the compressor. What that really means is that the enthalpy change across the compressor equals the enthalpy change of the fluid as it flows across the turbine. And that's really what we're saying here. H4 minus H5 equals H3 minus H2. But further, we can approximate changes in enthalpy as Cp delta T. So we could write a relationship between the temperatures around the turbine and the compressor. T4, 5, 3, and 2 are related this way. These equations are well worth writing down near your cycle diagrams in your book for the jet propulsion cycle. And of course, please understand, these don't apply to any other cycle, obviously. They don't apply to the gas turbine cycle, for example, because the purpose of the gas turbine engine, or the Brayton cycle, is to generate some shaft work, right? To turn something, output power that way. That's not the case here in the jet engine. Now, if we're interested in efficiency, there's not really a good way to go through thermal efficiency and put in all our energy balances and come out with something that means anything as we did before. One of the reasons for this, if you think about a jet, think about a jet just sitting still on the runway, whether it's on a ship or on land, wherever it be, and its engines are idling, or let's even say that you increase the thrust, but the wheels are captive, where the jet can't move forward. Well, you might be burning a lot of fuel, you might be tossing high velocity air out the back of the jet, but you're not going anywhere. So there's no valuable work. The reason for making the engine is to push the craft through the air, right? That's the purpose of the jet engine. If the craft's not moving, then you're just burning fuel, right? There's a zero efficiency. So it doesn't make sense to talk about efficiency as we normally would. Rather, we'll talk about propulsive power first of all. Propulsive power is just the thrust that's generated by the engine multiplied by the velocity of the craft. And this should make some sense to you, because you should know that power is equal to force times velocity. So if that's the case, and we can write an equation for the thrust, because what a jet really does is it brings in air at a low speed and tosses it out at very high speed. And basically you can think of it like a swimmer, right? That's kind of what a jet is like. It's pushing against a fluid, pushing that fluid backwards so it can go forward. And so the momentum change of the air is what provides thrust, and that's the equation here. If you remember this equation from dynamics, that's great. If not, that's where it came from, because all that's really happening is the air's momentum is being changed from the inlet to the exit, and we can write that as mass flow rate times the difference in velocity between the exit and the inlet. Then finally, if we write the propulsive power by plugging in this thrust, you can see the equation there at the end. The propulsive power is the mass flow rate of the air through the engine multiplied by the velocity change of the air across the engine, and then multiplied by the velocity of the aircraft through the air. Now be careful here. It turns out that the velocity at the inlet and exit of the engine have to be taken with respect to the same reference frame. In other words, if you're thinking of these velocities and measuring them while sitting in the jet, that's a different thing than measuring them on ground, right? Now, the difference between those two is the same regardless of whether you measure them in the jet or you measure them on ground. So it doesn't matter what frame you take, just make sure that when you're quoting these two or you're finding these two velocities, that they're taken with respect to the same frame, either a moving one on the jet or a still frame on the ground. But then the velocity of the aircraft has to be taken relative to ground, otherwise it doesn't make any sense. So this is the equation for propulsive power, and then propulsive efficiency can be written as propulsive power, which was what we want. That's the whole reason for making the jet engine in the first place, divided by the rate of heat input. So this is the first efficiency. It's still a thermal efficiency, but it's the first efficiency that involves a power ratio instead of an energy ratio. And it's just the nature of the beast that this is much easier to use and much more convenient for us.